Hello everyone. From this particular video, we will understand about two-dimensional stress problem, stress transformation, and Mohr circle. Now suppose this is one cylindrical body with tensile force F at both the end. Now if we think about one particular cross-sectional area, then this particular area will provide some resistance against the force. Now this particular force is actually normal to this particular plane. If we think about this plane, then the reaction of the force will also be normal. Because the force is normal, so the reaction of this force will be also normal. So now you can see that this will be the reaction for this particular force. The reaction force will be also equal to F, because as per equilibrium, both this force must be same, but this F force is actually distributed throughout this total area. So what will be the definition of stress? Stress will be actually F divided by A. But actually stress is the resistance per unit area. Stress is actually resistance per unit area. This will be stress. Normal stress. Normal stress, why you are saying normal stress? Because the force is applied with respect to the normal direction of the cross section. If we think about a cross section, the force is applied in the normal direction. So the resistance will be also in the normal direction. So that's why we are saying this is normal stress, and normal stress will be denoted by sigma. For any condition, it will be denoted by sigma. Similarly, this is another case. Here actually the force is not normal to the cross section of this particular body. If we think about this particular cross section, then this particular force is actually parallel to this particular plane, or we can say this is tangential to this particular plane. So the resistance will look like this. The resistance force will also be equals to F and will be in the opposite direction. As it is downward, so it will be upward. Both will be same. And stress will be equals to the resistance force divided by the area. And this stress will be termed as shear stress, because here actually the force is tangential to the cross-sectional area. So this stress will be termed as shear stress, and here shear stress will be denoted by tau. So tau means the stress will be shear stress. So if we think about one particular body, if we think about one cross-sectional area, if the force or the stress is normal to the plane, then it will be normal stress and it will be denoted by sigma. And if the stress is tangential to the plane, then it will be shear stress and it will be denoted by tau. So one will be sigma, another will be tau. So now this is one particular 3D element, and we have to understand certain notation, like what is sigma I. Sigma I, actually sigma I means it can be sigma x or sigma y or sigma z. Now sigma are actually sigma x, y or z, these are actually normal stress. If the normal stress is acting along x direction, it will be sigma x. If it is acting along y direction, it will be sigma y. And if it is acting along z direction, it will be sigma z. Now that is very simple. But what about the shear stress? What about the shear stress tau ij? This thing is very important. What is I and what is j? Shear stress will be always denoted by this type of term, tau ij. So what is I and what is j? I is actually the plane, and j is actually the direction. This thing we have to remember, that I is the plane and j is the direction. Like suppose consider this particular plane. If we think about this particular plane, the normal stress over this particular plane will be sigma x. Because if we draw normal over this particular plane, the normal will be along the x direction, or we can say positive x direction. Because this is the positive x direction, so the normal stress along this direction will be sigma x. And there can be different type of shear stress over this particular plane also. If the shear stress is acting along positive z direction, then it will be tau xz. Because this particular plane is the plane of x. Because if we draw the normal over this particular plane, then the normal will be actually along the x direction. So any type of shear stress which will be over this particular plane, always the first term will be x. Second term can be y, can be z, or can be anything else. When it will be y? When the shear stress is acting along y direction, it will be tau xy. When the shear stress will act along z direction, it will be tau xz. So this is tau xy because this is acting along y direction. Over plane x acting along y direction. So it will be tau xy. And this shear stress is over plane x but acting along z direction. So it will be tau xz. Similarly, if we think about this particular plane, if we draw one normal over this particular plane, the normal will be along the positive y direction. So the normal stress will be sigma y. This plane is plane of y. Now for shear stress, if the shear stress is acting along x direction, it will be tau yx, plane of y, direction x. And if the shear stress is acting along z direction, it will be tau yz, plane of y, direction z. Similarly, if we think for this particular face, the front face, if we draw normal over this particular plane, the normal will be along the positive z direction. The normal over this particular plane will be along the positive z direction. So the normal stress is sigma z. Now if the shear stress is acting along x direction, it will be tau zx. And if the shear stress is acting along y direction, it will be tau zy. So this is very simple. Same like the previous case, this is very simple. Now you can also ask that what will happen if the shear stress is acting not along this direction, in place of this direction, suppose it is acting along this direction. Like we are saying that what is tau xz? Tau xz is over plane x and acting along z direction, positive z direction. So what we can say if the shear stress is acting in the opposite direction? If it is acting on the opposite direction, it will be also tau xz, but here it will be minus tau xz. Because for this plane, if we draw the normal is along the x direction, positive x direction. So this plane is the plane of positive x. So for this plane, if the shear stress is also acting along some positive direction, either either z or either y, then it will be tau xz or xy. But if it is acting on opposite direction, it will be minus tau xz. And in place of this tau xy, if it is acting on this direction, it will be minus tau xy. So this is the concept. Now again, one thing we have to remember, this is for the opposite plane. Like if we think for this particular plane, the leftmost plane, we can say, here actually for this plane, if we draw the normal will be along the positive x direction. But if we draw the normal for this plane, this will be along the negative x direction. So this is the opposite plane, this will be along the negative x direction. So this plane, we can say this plane is negative plane. So for negative plane actually, we will consider the direction also as negative. Like for this plane, this is the plane of x, because if we draw the normal over this plane, the normal will be along the negative x direction. Now for this plane, if the shear stress is acting on the negative y direction, this is the positive y direction. If the shear stress is acting along the negative y direction, then it will be tau xy, because this is the negative plane, and for negative plane, all the direction will be negative. Sigma x will be negative, tau xz will be also negative, tau xy will be also negative. Like for tau xz, for positive plane, the direction of tau xz was this. This was tau xz. But for negative plane, the direction will be also negative. Here also the direction will be opposite of this, and it will be like this. Similar for these two plane also. These two plane also, this will be also, the logic is similar. So what I am trying to say here is that if we suppose think for these two plane, this is positive x plane, this is positive x plane, and this is negative x plane. This is negative x plane. So for positive x plane, if the shear stress is acting along positive y, then it will be tau xy. And if it is acting along positive z, then it will be tau xz. Similarly, for negative plane, if the shear stress is acting along negative y direction, then it will be tau xy. And if it is acting on negative z direction, then it will be tau xz. So this is the logic. Now again, if you can say that what will happen if the shear stress is not along this direction, if it is here, suppose the shear stress is acting on this direction, negative z direction for the positive plane, then it will be minus tau xz. Negative z direction for the positive x plane, so it will be minus tau xz. Similarly, for the negative plane, normal convention is that for negative plane it will be negative direction. But suppose for this particular negative plane, for this negative plane, if the shear stress is acting along positive direction, then also it will be minus tau xz. So for if I repeat, then actually I can say that for positive plane and positive direction, this will be positive. For negative plane and negative direction, this will be positive. But if for positive plane negative direction or negative plane positive direction, this will be actually negative shear stress. This will be positive condition, this will be negative condition. So that we have to remember for three-dimensional stress condition. Now another thing we have to also remember, this is not applicable for all case, but normally tau ij means shear stress, I is the plane and j is the direction. But sometime it can be also written as tau ii. If it is written tau ii, then actually it is not shear stress. That means the plane is same and the direction is same. Suppose this is suppose for this plane, this is y plane, positive y plane, and if the direction is also y, then this is obviously it is not shear stress, it is normal stress. So tau ii actually means sigma I. So if it is tau yy, then obviously it is sigma y. And if it is tau yx, then obviously this will be the direction of tau yx, and this will be the direction of tau yz, shear stress. And if it is tau yy or tau xx or tau zz, then obviously it will be normal stress. Now again, for the cylindrical body, what we have assumed? We assumed that the cross-sectional area for calculating the normal stress, we have said that sigma equals to force by area. But at that time when we have given the definition, we have considered that the cross-sectional area is actually the vertical plane, and the stress will be sigma x. If this is the x direction, then it will be sigma x. But it may also happen that due to this type of load, the failure is not occurring along this particular plane. If this is occurring on the vertical plane, we can say that this particular stress is very important. But it may also happen that the failure is occurring along some inclined plane, not vertical plane, which is at an inclined plane of theta. Theta can be anything. For vertical plane, theta is 0 degree. For inclined plane, theta can be from 0 degree to 90 degree, it can be any value. Any type of failure can happen. This may also failure like this. This type of crack can also develop. So we have to actually understand that what will be the stress for different type of cross-sectional area. Like if the inclined plane is at an angle of theta with respect to the vertical plane, if this is theta, then actually the cross-sectional area is not A. It is A by cos theta. So this particular area is more than A, and here also the stress will be different. So stress will be different. So if this particular stress is more than sigma x, then obviously it can be more critical for a particular condition. So we have to understand, we have to know that for which particular angle the normal stress or shear stress will be maximum. Because suppose for this case the normal stress is suppose 10 kilonewton per meter square or Newton per millimeter square, like this. But if suppose for a different condition it is 15 Newton per millimeter square, then it may happen that failure will occur not for this particular condition. Failure will occur for this condition, because for this case the normal stress is more or shear stress is more. That depends on the condition of the particular element. It can be brittle material, it can be ductile material, and based on that the condition that this particular material is more critical for which particular stress, that we have to know. But for different condition the failure can occur for different plane. and we have to know that for which particular plane the condition is more critical. Now suppose this is one particular two-dimensional stress element. This is one two-dimensional stress element. We can say that this is actually one particular special case of three-dimensional stress element with unit thickness. With unit thickness, if the thickness is 1, then three-dimensional stress element will actually transfer to two-dimensional stress element. So suppose this is direction x, this is y. Then for the normal stress, it will be sigma x, sigma y. These two are the positive plane. This is positive plane, so positive direction, it will be sigma x. This is also positive y plane. So here it will be sigma y. And these two plane are actually negative plane. This is negative y plane, because if we draw the normal will be along the negative y direction. So this is negative plane. For negative plane, we have to consider the negative direction. So this will be the direction of sigma y. And here also it is negative plane. So this will be the direction of sigma x. For shear also, this is positive plane. So tau xy will be along the positive y direction. This is the positive y direction. So this is the direction of tau xy. And this is the positive plane of y. So tau yx will be also along the positive x direction. So positive plane. These two plane are actually positive plane. Positive plane. So for positive plane, the direction of both these shear stress will be also positive. Tau xy will be along the positive y direction. Tau yx will be along the positive x direction. So these two plane are positive plane. And these two plane are actually negative plane. Negative plane. And for this negative plane, if the shear stress is acting along the negative direction, then it will be positive. And here also, if it is on the negative direction, it will be positive. So this is the direction of tau yx and tau xy. Now, mathematically it can be proved that tau xy and tau yx both will be actually mathematically equal. This is tau xy and this is tau yx. These two will be mathematically equal. Like suppose consider for this particular element, if we think that this particular length is p and this is q, then force developed due to xy, how much it will be? It will be stress into the area. Now stress is tau xy into the area. What will be the area of tau xy? Tau xy, this will be the area. So what is the area? I have already mentioned that the thickness will be 1. For 2D condition, the thickness we will consider as 1. And this particular length is q. This length is q. So tau xy into 1 into q. So this will be fxy. And what will be fyx? Fyx means this particular force. Here the force will develop. That will be fyx. Now how much will be fyx? Fyx will be equals to tau yx into the thickness is 1 into this particular length. This length is p. So into p. Into p. So this one is fxy, this is fyx. Now what will be mxy? Mxy means moment due to fxy. Fxy means force due to tau xy. Mxy means moment due to fxy. So how much will be the moment? It will be obviously fxy into the lever arm. This distance between these 2 points of tau xy, this distance, this is the lever arm. So this is p. So fxy into p. So mxy will be how much? Fxy into p. So that means we can say that mxy is actually tau xy into 1 into q into p. Into p. Similarly, what will be myx? Myx is actually the moment due to fyx. Now this is the position of fyx. The distance is how much? The distance is p. This particular, sorry, the distance is q. This distance is q. So this is q. So how much will be myx? Fyx into q. And the moment that will generated will be clockwise movement. Here due to this type of force, it will generate clockwise movement. And here it will be anticlockwise movement. For these two force, it will be anticlockwise movement. So this is anticlockwise movement and this is clockwise movement. Now, based on the concept of equilibrium, we can say that these two will be same. Total clockwise movement will be equals to total anticlockwise movement. And if both these two values are same, then actually it will be in a condition of equilibrium. So mxy will be equals to myx. So if both these terms are same, if these two terms are same actually, then it will be for both this term there is p and q. So tau xy will be equals to tau yx. Tau xy will be equals to tau yx. And these two terms are known as complementary shear stress. This is very important. Tau xy will be equals to tau yx. Or in general, I can say that tau ij will be equals to tau ji. These two terms are known as complementary shear stress. If one is there, another will be always there. And both the term will be actually same. So tau xy and tau yx both will be same. And we can actually use them interchangeably. We can use one in place of another. So this is one important thing. So in place of tau yx, we can also use tau xy. Both this thing will be same. But what if we have to consider a separate coordinate system? Like in place of x and y, it may also happen that the normal stress or shear stress is more in one particular different direction, different plane. Like in place of, as previously I have said that in place of the vertical plane, the crack may occur in a particular inclined plane. At that time, in place of this particular direction of stress, we have to analyze the stress in this particular direction. So that thing is also very important. That if the coordinate system is different or if the direction of stress is different, then that thing we have to also calculate. Because stress is actually based on the direction. Direction is very important. That from which particular perspective we are actually looking for this particular stress condition. If we are visualizing in a particular different direction, then the stress will be very much different. So we have to know, we have to understand the stress for different direction, not a particular direction. It may happen that this is the value of sigma x, sigma y. Suppose this is 5, this is 4. But it may happen that for a different direction, the value is 6, more than 5. So in place of 5, if it is more, then crack may occur in a particular different direction. That direction will be more important than this particular direction, vertical direction. So we have to know, we have to understand the stress for different direction actually. So all directions are important. So these are the different equations for calculating the value of normal and shear stress for different direction. If the coordinate system is changed, if there is some transformation of the coordinate system in place of x and y, if the coordinate system is rotated by an angle of theta, suppose we have rotated both the x-axis and y-axis by an angle of theta. If both these angles are theta actually, if this is theta, this is also theta, then actually the equations of stress will change. And this derivation is actually there in every book of strength of material. You will get these particular equations for calculating the value of normal and shear stress for different direction. Sigma x, sigma y and tau xy are actually the stress corresponding to 0 degree angle. Sigma x, sigma y and tau xy are actually corresponding to the xy direction. But for different direction, if this is x dash and y dash direction, then actually the value will change, and that value will get from this particular equations. And apart from sigma x, sigma y and tau xy, the only thing which actually changes the value of normal and shear stress is actually theta, the angle. This particular angle is very important. It can be 0 degree, it can be 90 degree, or it can be anywhere in between. If the value of theta is different, for different value of theta, we will get different value of stress. It can be any value, theta can be anything. Suppose consider this is the vertical plane, this is the plane of sigma x. For a plane which is at an angle of theta, this is the theta, then it will be sigma x dash. So that value we will get from this particular equation. From this particular equation, we will get the value. This is the equation. And this is the plane of sigma y. And if we rotate this plane by an angle of theta, then it will be the value of sigma y dash. That value we will get from this equation. and this is the equation of tau x dash y dash. So if we know the value of sigma x, sigma y, tau xy and theta, then we will get the value of normal and shear stress for any particular angle. For any particular plane, we can actually calculate, we can actually determine the value of normal and shear stress from these particular equations. Now, this particular thing is also very important, like what is the maximum value of sigma x dash. Like I have already mentioned that suppose this is sigma x acting along the positive x direction, and suppose this is sigma x dash, which is at an angle of theta with respect to the vertical plane. So sigma x dash can be any value depending on the value of theta. If theta changes from 0 degree to any value, it can be more than 90 degree also. Like suppose a plane is like this, then this will be the theta. If a plane is like this, then actually this will be the theta. In the same convention, this will be the theta. So theta can be anything. With respect to the vertical plane, if the plane is like this, then this will be the theta. So theta can be actually any value. Theta can be anything. Based on different value of theta, the value of normal stress will also change. Now we have to find out that for which particular angle the value of normal stress will be maximum. Now I am not going in the details of the calculation. But you already know that actually for finding out the maximum or minimum value of normal stress, we have to differentiate the value of sigma x dash with respect to theta, because sigma x dash is actually one function of theta. So if we differentiate this particular value, if we take the derivative and if we make it equals to 0, then we will get the particular value of maximum or minimum value of normal stress. So we can actually calculate the derivative of this particular value. So it will be like this. If we take the derivative of this part, this is constant, so it will be 0. Then this is the constant term, then cos 2 theta, the derivative will be 2 into sin 2 theta. And again this is the constant term tau xy, and for sin 2 theta the derivative will be 2 into cos 2 theta. And it will be 0 for the maximum point. And for that particular point, we are saying that theta equals to theta p. For that point with maximum value or minimum value of normal stress, we are saying theta equals to theta p. Then if we rearrange the term, it will be tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. And from this value, we can calculate the value of sin 2 theta and cos 2 theta. This is very simple actually. If we think about one triangle, then if this is 2 theta and this is 2 tau xy and this is sigma x minus sigma y, then for this triangle tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. Now what will be sin 2 theta p? Sin 2 theta p will be height by hypotenuse. So this particular hypotenuse value will be root this square plus root this square. This is the value of hypotenuse. Root sigma x minus sigma y square plus 2 tau xy square. So this will be the value of hypotenuse. So this will be sin 2 theta p. And cos 2 theta p will be same, base by hypotenuse. So sigma x minus sigma y by root this total value of hypotenuse. So this will be cos 2 theta p. Now you may ask that why plus minus? Because it can be, both can be plus actually, then also this logic is valid. Tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. This is valid when both are positive. This is also valid when both are negative. If both these values are negative, then also the ratio will be, if both are negative, then also the minus will be cancelled out and this equation will be also valid. So for plus this is also valid, for minus this is also valid. So that's why this plus minus term is there. And if we put this value of cos 2 theta p and sin 2 theta p in this particular equation, then actually we will get the value of maximum normal stress and minimum normal stress. So this is very simple equation. If we just put this two value of sin 2 theta p in this particular area position, and if we put this particular value of cos 2 theta p in this particular position, then after doing all the calculation, we will get the value of maximum normal stress and the minimum normal stress. So this is the simple calculation. This is the simple calculation. So maximum we are saying sigma 1 and minimum we are saying sigma 2. This stress is known as, these two terms are very important. This is known as major principal stress. Major principal stress. And this particular term, this is known as minor principal stress. Minor principal stress. One is major principal stress, another is minor principal stress. And by applying the similar logic, we can also calculate the value of maximum or minimum shear stress. The logic is again similar. This is the equation of shear stress. For getting the maximum or minimum value of shear stress, we have to differentiate this particular value with respect to theta. So if we differentiate with this particular value with respect to theta, and if we make it with equals to 0, then it will be either maximum or minimum. This is the logic of maximum and minimum. We know that it can be maximum or minimum if the derivative with respect to the function is 0. Here actually tau x dash y dash is also one function of theta. So if we just differentiate this particular value with the independent term theta, then we will get the either maximum or minimum value of shear stress. So if we just differentiate this particular term, then this is the constant term, this is the constant term, and sine 2 theta, the derivative will be 2 into cos 2 theta, and here tau xy, the derivative of cos 2 theta will be minus 2 into sine 2 theta. So if we rearrange this term, then the shear stress will be, then the angle will be tan 2 theta s will be minus sigma x minus sigma y by 2 tau xy. So this will be the particular angle, this will be the particular plane for which shear stress will be either maximum or minimum. So again we have to calculate the value of sine 2 theta s and cos 2 theta s. Again we can simply from the triangle, if this is 2 theta s and this is minus sigma x minus sigma y, and this is 2 tau xy, then hypotenuse will be this, then sine 2 theta will be height by hypotenuse, so this will be the value, and cos 2 theta will be base by hypotenuse, so this will be the value, and this can be plus minus like the previous case. This can be plus minus because if in place of this, if this is minus of minus sigma x minus sigma y by minus 2 tau xy, then also if both are minus actually, then also this equation is valid. Both are minus actually, when this is already minus, so minus of minus, this is plus. So both, if both these terms are actually minus, then also this equation is valid. So for that reason there are plus minus value, and again if we put this two value, this value of sine in this particular equation, and if we put this value of cos in this particular equation, and if we do the calculation, then we will get the maximum or minimum value of shear stress. Then we will get the maximum or minimum value of shear stress. So this is one very important thing. Now these are two graphs. This one is the graph of normal stress sigma n, and this is the graph of shear stress. This is the graph of shear stress for a particular value of sigma x, sigma y and tau xy. This is the graph, and here you can see that this is actually the point of maximum normal stress. So we can say this point is actually the major principal stress. This is the point of major principal stress because this is the maximum value of normal stress, and this point is actually the minimum value of normal stress. So this will be sigma 2. This is the point of minor principal stress. This is the point of minor principal stress. And if we look for these 2 points, then actually their gap will be 90 degree. Their gap will be 90 degree. That means that if we consider two different plane, if this is the plane of major principal stress, then this will be the plane of minor principal stress, and these two will be perpendicular. These two will be perpendicular, so their gap will be 90 degree. Their gap will be 90 degree. And another thing is also very important. Here you can see that when there is a normal stress maximum or minimum, at that point you will find out that the shear stress is 0. For maximum also shear stress is 0. For minimum also the shear stress is 0. So for the point of maximum or minimum normal stress, shear stress will be 0. So for major or minor principal stress, when the stress is either major principal stress or minor principal stress, then this plane will be termed as principal plane. This plane will be termed as principal plane, and for this principal plane, shear will be 0. Shear stress will be 0. Shear stress will be 0. Because here you can see that for this 2 point, the shear value, this is 0. This point is 0. So this will be 0. 0. So this is the case. Now what about the maximum and minimum shear stress? Here you can see that for this point actually, for this point, here actually for this point, shear is maximum, tau max, and almost for this point, tau is minimum. Tau is minimum. And if you look this particular value, this tau max will be close to, this is 50, so this will be almost 55. And tau min will be almost minus 55. Minus 55. So these two are actually, the value is equal, but it is opposite in sign. And the difference between these two plane are actually 90 degree. So again, the plane of maximum shear stress and the plane of minimum shear stress, these two plane are actually perpendicular to each other. And another thing is also very important here actually. This plane, the plane of maximum shear stress and minimum shear stress, this gap is 90 degree, but the gap between maximum normal, minimum shear, and then minimum normal, then maximum shear, all these gaps are actually also 45 degree. These gaps are 45 degree. That means these two are the plane of maximum and minimum normal stress. But the plane of maximum and minimum shear stress, their gap, this gap will be 45 degree. This will be 45 degree. 45 degree. This gap is 45 degree. This will be this blue color, this will be the plane of maximum and minimum shear stress. So this gap is 45 degree in between them, and the total gap, the plane of maximum normal and minimum normal, and the plane of maximum shear and minimum shear, their gap is 90 degree. This gap will be 90 degree. So this is the concept. Now it will be easier for you to understand if we go for a graphical method, and that graphical method is very important, very interesting, and very useful from all analysis point of view, all structural analysis point of view. And this is very important also for geotechnical engineering. For geotechnical engineering also, this particular graphical method is very important, and this is known as Mohr circle. Very important term, Mohr circle. And if you understand Mohr circle, then this stress concept will be very much easier for you to understand. Mohr circle is very important. Now we know that what is the equation of normal stress? We can say sigma x dash or sigma n. The equation of normal stress for any particular angle is actually this: sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So let us take this as this, consider this as A, this is B, this is C. So it will be A plus B cos 2 theta plus C sin 2 theta. Sin 2 theta. Now what is the equation of shear stress? Tau. The equation is minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Cos 2 theta. So it can be written as this: minus B sin 2 theta plus C cos 2 theta. Same like this case. Sigma x minus sigma y by 2, this is B, and tau xy, this is C. So now if we rearrange this term, sigma n minus a, that is equals to b cos 2 theta plus c sin 2 theta. And how much is tau? Tau is minus b sin 2 theta plus c cos 2 theta. Now if we just square both this term, if we square this term and if we also square this term, then what will be the equation? Then it will be, if we square these two terms and if we sum it, then it will be look like this. Then it will look like this: sigma n minus a whole square plus tau square equals to b square cos square 2 theta plus c square sin square 2 theta, then 2bc cos 2 theta sin 2 theta, then plus b square sin square 2 theta plus c square cos square 2 theta minus 2bc sin 2 theta cos 2 theta. So these two terms are actually same. These two terms are same. So finally it will look like this. Finally the term will look like this. This term will be sigma n minus a tar whole square plus tau square equals to b square cos square 2 theta plus b square sin square 2 theta. So it will be b square. Then c square sin square 2 theta plus c square cos square 2 theta. So it will be plus c square. So this will be b square plus c square. Now if we just rearrange this term, it will look like this. We know what is a. A is actually this is sigma n minus a is actually sigma x plus sigma y by 2 whole square plus tau square equals to how much is b? B is sigma x minus sigma y by 2 whole square, and c is tau xy. C is tau xy. So plus tau xy square. So this is nothing but a equation of a particular circle. This is the equation of a particular circle with this form: x minus a whole square plus y minus b whole square equals to r square. This is the term of a particular circle. So this is the equation of a particular circle. And now what is this means? This means that suppose this is x coordinate system, this is y, then the center of the circle will be AB, and the radius is r. So for Mohr circle, actually, if we think about Mohr circle, then this is A, B is 0. Here there is no term, so B is 0. So there will be one Mohr circle whose center will be sigma x plus sigma y by 2, 0. And its radius will be how much? Radius will be r square, so it will be like this, root square. So the radius of the Mohr circle will be root sigma x minus sigma y by 2 the whole square plus tau xy square. So this will be the radius of the Mohr circle, and this will be the center of the Mohr circle, because this term is same with A, and for B there is no term, so it is 0. B is 0. So this will be the equation of Mohr circle. This will be the concept of Mohr circle. Now if we go for the details, then it will be easier for you to understand that how to form the Mohr circle and why Mohr circle is so much useful. Now normally for Mohr circle, when we are constructing the Mohr circle, the normal stress will be along the x-axis and the shear stress will be along the y-axis. But for different convention, actually for different case, we consider different type of thing. But suppose for this particular condition, we are considering that this is the direction of positive tau. That means if it is in that direction, then it will be negative tau, and here it is positive tau. And this is the direction of positive sigma, positive normal stress. For different book, for different type of case, this convention can be different, but here we are considering this only. Now suppose these are the condition of stress. Suppose this is one particular element, 2D element. This is the direction of sigma x, sigma y, and this is suppose tau xy. This is tau xy. So this is the case. So there will be 2 points actually. This is one point, this is another point. this point is sigma y minus tau xy. So this point is actually the stress of the horizontal plane. The stress of the horizontal plane. Here actually sigma y is positive. We are considering here the tensile stress as positive. Or we have already mentioned that if sigma y is like this, then it is positive, and sigma x is like this, then it is positive. So this particular point is actually the point with plus sigma y. And why minus tau xy? Because this stress, this tau xy here, this stress is creating actually one clockwise rotation. And we are considering here that clockwise rotation is negative, anti-clockwise is positive. So here this stress, this tau xy for this two horizontal plane, this tau xy is actually creating clockwise movement. So we are considering this as negative. And this is for the vertical plane. This point is actually corresponding to the vertical plane. For vertical plane, this is sigma x. And here actually the shear stress is creating anti-clockwise movement. Here shear stress is creating anti-clockwise movement, and anti-clockwise movement we will say this is positive. So it will be plus tau xy. And I already mentioned that plus tau here will be considered downward, and minus tau we will consider upward. So for this two vertical plane, the point will be sigma x tau xy. For horizontal plane, it will be sigma y minus tau xy. So these are the 2 points. So first we have to draw these 2 points. First we have to draw these 2 points. These 2 points. Now we have to connect these 2 points. If we connect these 2 points, then we will get the center of the Mohr circle. And as I have mentioned in previous derivation, that the center of the Mohr circle will be sigma x plus sigma y by 2 and 0. Obviously for these 2 points, the middle point will be sigma x plus sigma y by 2, and tau xy plus minus tau xy by 2, it will be 0. So this is the center of these 2 points, and this will be also the center of the Mohr circle. So we will consider this point as the center of the Mohr circle, and taking this as the radius of the Mohr circle, we will draw the Mohr circle. So this particular circle will be Mohr circle. This will be Mohr circle. Mohr circle. And the radius of the Mohr circle will be this. As I have already derived it, this is the radius of the Mohr circle. Now suppose for in place of this particular vertical plane of sigma x, sigma y and tau xy, if we consider a plane which is at an angle of theta with respect to the coordinate system, if we consider another particular stress condition which is at an angle of theta, then the stress will actually change. The stress will actually vary. The stress will actually change, and then these 2 points will be rotated by 2 theta in the anti-clockwise direction. And we are only considering the rotation in anti-clockwise direction. Here we are considering both as rotation in the anti-clockwise direction, and we are considering anti-clockwise direction as positive. If it is clockwise rotation, then it will be negative. It will be in this direction. So actually the new stress, this will be the new stress. This will be sigma y dash and minus tau x dash y dash, and this will be sigma x dash tau x dash y dash. So in that way we have to rotate these 2 points. Rotate these 2 points for different value of theta, the rotation will be different. If theta is increased by certain amount, this point will change and will come here. So these 2 points will pair of point will actually move over this particular circle. These 2 particular point will move over this particular Mohr circle. So this is the concept. This is the concept. Now after certain time, these 2 points will come here in these 2 positions, and obviously these 2 points will be the point of major and minor principal stress, because here you can see that for this 2 point, this point, normal stress is actually maximum. For this Mohr circle, there cannot be any point which is more right from this particular point. This point is the rightmost point. If we consider any point here over the Mohr circle, for this particular point actually sigma is maximum. This particular value is actually maximum sigma, because for no other point the sigma can be more than this, and for no other point sigma can be less than this for this point. This will be sigma mean. This will be sigma mean. So this is sigma max, this is sigma mean, and for both these 2 points, tau is 0. Because for these 2 points are actually over the x-axis, over the sigma axis. So for these 2 points, there is no value of tau. So again we can say that for the case of major and minor principal stress, the value of tau will be 0. So for these 2 points are actually the point of major and minor principal stress, and for these 2 points, shear stress is 0. Shear is 0 for these 2 points. And what is the difference between these 2 points? What is the angle? If we think about these 2 points, their gap is actually 180 degree. Their gap, these 2 points, the gap is actually 180 degree. And what we are already saying in Mohr circle, that we are considering 2 theta. We are always considering 2 theta for Mohr circle. Now the gap between these 2 points is actually 180 degree. So 2 theta is 180 degree. So theta is actually 90 degree. So the gap between the major and minor principal stress, their angle is actually 90 degree. 2 theta is 180 degree. So theta will be 90 degree. So this is the concept, that major and minor principal stress, their angle will be 90 degree. And for both major and minor principal stress, the shear stress will be 0. And another thing is also very important, that what will be the difference between major and minor principal stress? This difference will be actually the diameter of the Mohr circle. The diameter of the Mohr circle is actually sigma max minus sigma mean. So what is the radius? Radius is actually sigma max minus sigma mean by 2. So this is the radius of the Mohr circle. So these two values will be same. The radius of the Mohr circle will be sigma max minus sigma mean by 2. And this particular thing is also very important. This will be required for calculating different particular case, particular problem. We have to remember that the radius of the Mohr circle will be sigma max minus sigma mean by 2. And one thing we have to also remember, that this particular point is our vertical plane, and this particular point was our horizontal plane. So what is the difference between the angle of major principal plane with respect to our vertical plane? In Mohr circle it is 2 theta p1. So actually it will be theta p1. For Mohr circle it is always double. The angle will be double. But here actually the gap between the vertical plane and the plane of major principal stress is 2 theta p1. So here it will be theta p1. If we consider theta p1 angle, then actually we will get the plane of major principal stress. And what is the angle between the vertical plane and the minor principal plane? That is actually 2 theta p2. And the gap between 2 theta p1 and 2 theta p2, this gap is actually, in Mohr circle, this gap is actually 180 degree. So theta p2 and theta p1, this gap will be 90 degree. So this is theta p1, this will be theta p2. So these two plane will be the plane of major and minor principal stress. This will be the plane of major and this will be the plane of minor. And their angle will be like this. And this angle we will also get from the Mohr circle. From Mohr circle actually we will get the value of 2 theta p1 and 2 theta p2. And from this value actually we can very easily, we can calculate the value of theta p1 and theta p2. The gap between theta p1 and theta p2 will be 90 degree. So these two are actually the plane of major and minor principal stress. This is the minor and this is the major. And these are the angle. Now these two are actually point corresponding to maximum and minimum shear stress. Because here you can see that for this particular Mohr circle, for this point only, tau is maximum or minimum. Here actually for any other point, this will be the tau value. For this point, this will be the tau value, this will be the tau value. But here actually for this particular point, the tau value will be either maximum or minimum. Here actually tau max, we are considering this direction negative tau and this direction positive tau. So this is actually the point of a maximum tau and this is actually the point of minus tau. But minus actually means the direction. That is not very important. But numerically, for this particular point, tau is maximum and maximum. For both these 2 points, tau value is maximum or minimum. Mathematically, the value, if we consider the value, both are actually maximum. And what is this value? The value of tau max or tau min, what will be the value? The value will be actually the radius of the Mohr circle. The value of maximum or minimum shear stress, the value of will be radius of Mohr circle, and obviously the radius will be sigma max minus sigma min by 2. Minus sigma min by 2. So if we know the major and minor principal stress, then major minus minor by 2 will be the maximum or minimum value of shear stress. Maximum and minimum value of shear stress. And we have to remember one thing, that when shear stress is either maximum or minimum, normal stress is actually the average stress. Normal stress is actually the average stress, because this is the center of the Mohr circle. And for center of the Mohr circle, we know the coordinate is sigma x plus sigma y by 2, 0. So actually, when we will get the maximum or minimum value of shear stress at that 2 point, the normal stress will be sigma x plus sigma y by 2. Or it can be also sigma max plus sigma min by 2. That value will be also same. Max plus sigma min by 2. This value is equals to sigma x plus sigma y by 2, because this is sigma average. For any 2 point, we can consider any 2 point in the Mohr circle, their average will be sigma x plus sigma y by 2, because that is the center of the Mohr circle. We can consider any 2 set of point. We can consider any 2 set of point, their average will be actually the center of the Mohr circle. So that value is actually sigma average. So when we will get the maximum or minimum value of shear stress at that 2 point, actually normal stress will be sigma average. Sigma average. So that is also very important thing. And another thing we can actually clear from the Mohr circle, actually the angle between the vertical plane and the major and minor principal plane, their gap was 90 degree. We have already said this, that their gap will be 90 degree, because this angle is 180 degree. So actually it will be 180 degree by 2, so it will be 90 degree. Now when we will consider the plane of major principal stress and the plane of minimum shear stress, their gap is actually in Mohr circle, it is 90 degree. So in actual case it will be 90 degree by 2, so it will be 45 degree. The gap between these 2 points, these are in Mohr circle, it is 90 degree. This gap between these critical cases, this gap is 90 degree. Minor principal, minimum shear, major principal, maximum shear. All these gaps in Mohr circle is 90 degree. So for real life case, all this gap will be divided by 2. So the gap will be 45 degree. For all this case, the gap will be 45 degree. So this is also very important. So this will be 2 theta s1 and this will be 2 theta s2. And their gap is, obviously their gap is, in Mohr circle the gap is 180 degree. So in real life it will be 90 degree. So this will be the 2 plane. This will be the plane with maximum shear and this will be the plane with minimum shear. So this is the concept. They will be perpendicular to each other. They will be perpendicular to each other. Now this is another very important and interesting concept with respect to Mohr circle, and this is very much useful for geotechnical problem actually. This is mostly used in geotechnical problem. The concept of pole. This is also very important. Like this is suppose our Mohr circle, and we know that these 2 are our point. This point is actually point corresponding to the vertical plane, and this particular point is point corresponding to the horizontal plane. So if we consider a particular 2-dimensional stress element, this point is vertical plane sigma x tau xy. So sigma x is positive, means it is actually tensile in nature, and tau xy is also positive. So tau xy positive means it will create anti-clockwise rotation. So it will look like this. So this will be the direction of tau xy for the vertical plane. For the vertical plane, this will be the direction of tau xy. It will create anti-clockwise rotation, and here we are actually considering that anti-clockwise rotation is positive. Now what for this particular point? This point is corresponding to the horizontal plane. There actually stress is sigma y minus tau xy. So this will be sigma y. And why minus tau xy? Because shear stress will create clockwise rotation. So it will look like this. So this will be minus tau xy. So this is actually the sign convention, that for shear stress, when it will create anti-clockwise rotation, it will be positive, clockwise rotation it is negative. So these two are our actually point. These two are our point. Now, what I have already said, that if our plane is actually rotated by theta, if we consider one particular coordinate system which is rotated by an angle of theta, suppose this is the first coordinate system xy. If these 2 points are actually rotated by an angle of theta, then actually these 2 points in the Mohr circle will actually rotate by 2 theta. I have already said this, that when these 2 points will rotate, the coordinate system will rotate by theta, these 2 points will actually rotate by 2 theta. So this 2 point has rotated by 2 theta, and from Mohr circle actually we will get the new value of normal and shear stress. From the graph actually we can, from Mohr circle actually we will get the actual value of normal and shear stress for these two different points. For these two different plane we will get the value of normal and shear stress from the Mohr circle. So this is actually the rotating the particular these 2 points by an angle of 2 theta. Rotating this two particular point by an angle of 2 theta in the anti-clockwise direction. So this is one particular method. But apart from this actually, another method is also there which is very important and which is very effective also. In place of rotating this 2 point by 2 theta, we can use this particular concept. This is the concept of pole. First, these two are our point. One is sigma y minus tau xy. This is the stress corresponding to the horizontal plane. And this is another point. This is sigma x tau xy. This is actually the stress corresponding to the vertical plane. So these two are our point. Now from these 2 points, this is actually our horizontal plane and this is our vertical plane. So from horizontal point, we will actually draw one line which will be parallel to the plane, because this point is the point with respect to the horizontal plane and this point is point with respect to the vertical plane. So with respect to this particular point, we will draw one line which will be parallel to the plane. This is horizontal plane, so we are drawing one horizontal line. This is for vertical plane, so we are drawing one vertical line. And this two particular line is cutting the Mohr circle in this particular point. And this point will be termed as pole. This point is termed as pole, and this particular pole is very important. If we can identify the pole, then after that, the concept is very simple. If we can identify the pole, then from pole, we have to just draw the line parallel to the plane. We have to just draw the line parallel to the plane. Suppose this is the plane, so we have to draw one line parallel to the plane, and this is another plane, so we have to draw another line with parallel to this particular plane from the pole. From the pole, if we draw these two lines, then we will again get the new value of normal and shear stress. So we can either rotate this 2 point by 2 theta, or we can actually use the concept of pole. Like first we have to identify the pole. If we can identify the pole, from pole, if we just draw the line parallel to the plane, suppose there is two plane like this, two 90-degree plane like this, we have to just draw the parallel of these two plane. Parallel of these two plane if we can draw, then we will get the value of normal and shear stress for that particular point. So that is the concept of pole. First we have to identify the pole, then we have to draw the line parallel to the plane. And obviously this particular angle will be theta. This angle is theta, and from basic geometry we know that that center angle, this is actually central angle. Central angle is actually twice of the inscribed angle. If there is same arc, we know that this is central angle. Central angle is actually twice of inscribed angle from the basic concept of geometry. So obviously this thing will happen. This thing will happen. This is theta. So obviously the central angle, this will be 2 theta. This will be 2 theta. So this is 2 theta. So if this is theta, obviously this will be 2 theta. So the logic is actually same. Logic is very simple. But in place of this rotating by 2 theta, we can actually use the concept of pole for actually getting the stress for a new point. So if this is the new point, for this there will be new value of normal stress and shear stress. We can easily calculate that from Mohr circle. So this is all. This is all. Hope you have able to understand that how to use Mohr circle for doing the transformation of stress. If you have any type of question, then you may ask that in the comment box. Thank you for your attention. Thank you.